up here, had some surgery, and it took a long time for his head to clear, just because of the strength of the medication. It just took a long time for the body to get it out. I remember having that kind of issue. So, but anyway, so I asked for the half-life after the elimination. And then finally, the fun one is if the drug were administered continuously and not stopped, okay? What would be the steady state concentration of the steady state? Steady state concentration of B. What's a steady state concentration of B? Now this is the drug outside the blood, this is the drug in the blood. So I'm looking for the steady state concentration of B, or when this is equal to 0. And if you have successfully done part B, it becomes an trivially simple problem. Do on fingers. Okay? But I wanted to guide you through that. But it's an interesting actual application. And try to remember the what's the enzyme that breaks down the ethanol and get too hammered the previous time. Alcohol is it like ethanol dehydrogenase, I think it's called, something like that. Anyway, there's kinetics are very well known on that. And being very well informed on the kinetics and the nature of the enzyme and the elimination processes, that'll help you to survive a breathalyzer test if you need be. All right. Any other problems you want to ask about? Okay. Just kind of thinking back on some of an overview now. We started with the whole approach has been get some fundamental definitions in place, orders, how to define the rate of a reaction. And then what we wanted to do then first was to go into the laboratory and determine what a rate log was. We had a variety of different additional techniques that I introduced that are not generally introduced in a general chemistry course. We had the abysmal trial plotting method that they do in some gen chem courses. But then you had the method of initial rates. This you can go to any gen chem book and practice if you like, because they all have. They have the method of initial rates. Of course, I tweaked it just a little bit. We had one that was algebraically a little bit more deft, and most of you negotiated it quite well. And then I introduced other style methods. Now, all of these had in their place, they had an equation that was produced, either be it a half-life or pseudo-order with initial rates. And in each one of these instances, I produced an expression that was essentially in linear form. We did a big on that. Everything I tried to do was to put some equations within linear form. And in those equations will be provided for you. And one of the things you should have the skill to be able to do is if you see an equation, that it is what you would know how to plot. For example, we had a pseudo order with initial rates, so something like this. We had R was K, A to the n power, and I manipulated this to say, well, the log of the rate is in log of A plus the log of K. So that was one of them that we had actually done. That was a pseudo order with the initial rates method. So just given data, although you're not going to be asked to do any plotting, you're going to be asked to interpret a plot, something along that lines. But if I asked you questions such as this, what would I plot and how would I obtain the order and the rate constant for this reaction? What would you answer?
Y equals mx equals b.
Y is what? Well, yeah, that is correct, right? Y equal mx plus b, but what's y, what's x, what's m, what's b? It gets to the question. What would you plot?
When you take the natural log of the concentration and then the rate, or the natural log of the rate and plot this.
Okay, then with the natural log of the rate of the y-axis. Right. So if I made a natural log of the rate versus the natural log of the concentration. So it's exactly what he says. If I gave you concentrations and rates, you'd create an extra column of logs of each one of these things. By the way, what does not make any difference if you do, natural log or base 10 log or hexadecimal log, whatever you want. All right, so what would you associate then with the order of the reaction?
The slope.
The slope. So we have the m, we have the slope. That's what I mean by linear form. So if I wanted to calculate a k then for this reaction, which would be a pseudo-order k, how would I do it?
When you do the exponential of the intercept.
The common mistake to make is if you do make this association, and I gave you a graphic and I gave you an equation with the numbers in. I said, all right, for example, let's say I had this. The equation after I did the fit was 2 times, let me do it this way. We get 0.16. All right, so here's two mistakes, or here's a common mistake. You look at here and you say, well, that's log of k, and that's my intercept. So I say, well, what's k? Oftentimes, some say, well, k is the natural log of 0.16. You see? That's a mistake. Don't make that. One of you will. I'm going to laugh. All right. So, no, in this instance, that the 0.16 is the log of k. That's the association here. So to find the k, you have to untie that logarithm, do e to that power. Okay. So what we did was a fairly large section that was just that, just doing methodologies and kind of much better methods for determining. A lot of you got a little bit confused in that you were associating all of these linear methods, which we all put in linear form, with the trial plotting method. You're trying to find, like for example, you would take something like this and you would plot it 3 different ways as the trial plot. You were getting confused as to the methods. These are just as they are. So if I give you this, that's what your association is. If I use a trial plotting method, here he said 0, first or second order, you would do that. But the methods differ, so don't mix them up too much. We then went to temperature dependence, and we went back to the Arrhenius law and provided it in one of 2 forms. I can't remember. But we had something like this. The natural log of the rate constant was minus the activation energy over RT. Let me write it this way. R times 1 over T plus a constant. And then we had the 2-point version where I have a log of K2 over K1 as minus E of A over R times 1 over T2 minus 1 over T1. Like I said, I'll give you all these. All right? I'm not asking you to memorize these sorts of things. All right? So those were 2 different kits. Did it by chance go look at the crickets thing? It's kind of neat, isn't it? I like the other ones with the fireflies and all that stuff. But anyway, so it was kind of worked out that way. But so we just did, can you calculate K's or temperatures at different times, doing those sorts of things. Not too much along here. So see, a lot of this, there's less concept in this whole section as there was just kind of mechanics. How do you go about these things? So after we've gone through these different methodologies, we'll look at temperature dependence. Then we finally went down to, okay, we have gone into the lab, we have we have obtained our rate law that we've done by whatever method that we've done. And so now what we'd like to do is say, all right, given a reaction system, we want to try to devise a mechanism. A mechanism we can write rate laws for exactly, because a mechanism is always said to be elementary steps, steps that occur exactly as they are written. In an elementary step, you could always write the rate law, which is exactly what we've been doing. We said it's unlikely. There were 2 reaction scenes that we saw that were unlikely. One we saw for reaction, I think this was the product. So I said, well, can this be a reasonable elementary step? And give a few reasons why not. Couple. The biggest reason why not.
3-card collision.
three-body collision. But as soon as you said there's a three-body collision that is highly unlikely, the first part, then you can really kind of stomp on it and just pile on, if you like, dog pile, where you say things like, well, not only do they have to collide exactly at the same time, they have to be oriented in the right way, they have to be vibrating in the right way, they have to have the minimum energy in the right way, and all that just takes it down. Not to say that termomolecular collisions and reactions do not exist. They do. They are typically very, very slow. We had another reaction scheme when we were looking at iodine. It was a little bit more subtle. I had this reaction here, an iodine plus an iodine producing I2. I said that's impossible. We analyzed that. So why is that impossible?
There has to be something to take the momentum.
With the excess energy somewhere along the way, yeah. Because they're going to come together, they're going to form a temporary bond, and immediately bounce right on apart. So if they can come together and something can take that energy away, then we're okay. Now, by the way, that would not occur if I had, let's say, a polyatomic molecule. Let's say I wanted to form a dimer from this is one very common, two NO2s going to N2O4. All that is a dimer. It's just like this, but it's with NO2 instead of N2O4. This happens all the time. Now, this is very, very easy, no problem. And the reason why is that from our talk way back in heat capacities and energies, we know that bigger molecules have more places to store energy. So if I take molecules and bring it together, this has all kinds of vibrations to take that energy and spread it out. It's like having a single spring against the wall. Let's say I had a spring on the wall and I had a board. So I had my wall, I had a spring on here, and I had this platform here. Well, if I hit that spring, it just goes in, comes right back out. But if this has multiple springs all over, going in all different directions, it would be more likely to absorb a blow. You can think of it that way. So the same thing happens. So the fact that these are atoms is what made that impossible. So these are just little subtleties we learned about mechanics, about how things can possibly come together. Beyond that, we find that doing the mathematics for a complex mechanism, it just gets very arduous, very difficult to do. So we don't do that. So we introduced two approximation techniques, ones of which you're now currently working through. One is the steady state. We identify an intermediate. We say, we make the assumption the intermediate will build up, it'll hold at a constant concentration while the reaction is taking place, and then it will go away in the end. So we do steady state. We set the rate at which it appears, the rate at which it disappears, we add them all together, set it equal to 0, just like we opened up today. In the other method was a fast equilibrium approach. It says if I write a reaction mechanism and identify one of them as being a slow step, and we can do that for a variety of different arguments. You can argue one is a slow step by different schemes. But if I say I have, A going to B, A plus B going to C, and then C plus B going to E plus F, and F then decomposing to G plus H, and I keep writing, and I say this is slow. Stop here. Write the rate of that reaction, go home, right? Of course, if I have this extended, if I write this one as a slow step, ignore everything past that. That's your rate. You take that rate of that slow step, then you treat this one as in equilibrium, and then you set that forward rate equal to the reverse rate, and then you do very similar to a steady state. You find the intermediates, and then you solve for those. And that finished out what we had talked about throughout the entire kinetic. It was a very brief run through kinetics. When we come back, we're completely going a different direction. Talk about some really fun, interesting quantum and spectroscopy and how the world's really built up. And believe me, the concepts are going to bake your noodle. It baked people who are smarts noodle. It is. The concepts are very, very strange, but you'll have a good time with it, I promise. Anyway, so that was kind of the synoptic overview. There's not a ton, but just, like I said, mechanical stuff. So you will do a few more calculations on this exam than others, but nothing's going to be arduous and backbreaking, and you're not going to be bleeding from the ears or anything like that. You'll do fine. Get every bit of confidence. So I peek at one people, they have an exam right after you, and I can smell the anxiety. Yeah, we grow the tissues to sense that. It gives us a great deal of personal satisfaction. Anything else? Okay, all right, as I said, Wednesday I'll be around. We're not going to formally have anything. Of course, the exam release on Thursday morning, just doing kind of a mechanical type of thing. But one of the techniques that you use, bring that in. Except I will be down, of course, Wednesday to collect your homework, or if you want to bring it and put it in my office box or give it to the secretary, that's fine as well. Yeah.
Research day on Friday.
What's that?
Oklahoma Research Day.
Oh, thank you very much. I've been asking, please remind me. How many are affected by the research day on there? Just 2? And tell me about your schedule on that, on how that works.
No idea. We show up, we present sometime, we get to leave sometime that afternoon.
Yes, from what I understand, what it is there's just a duration of time, you'll have some sort of a presentation in place. And so it would not be outrageous for you to pop out for a short amount of time and then go back. But if that does cause a problem, all right?
It's in Tahlequah.
Oh, it was in Tahlequah.
Yes.
You didn't say, I thought it was over here.
No.
Oh, it's in Tahlequah. Okay.
Yeah.
So it just affects you two? All right. Right. All right. Let's talk about it, the rest of you.